Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists right here in our solar system, yet connects us to the infinite expanse beyond. Settle in, make yourself comfortable, and if you're watching this from your bed, perhaps dim the lights just a little. I'm curious to know where in the world you're joining me from tonight. Leave a comment below and tell me what time it is where you are. Are you watching this under the same stars that witnessed something remarkable just a few years ago? Perhaps you're in a city where the lights hide the stars, or maybe you're fortunate enough to be somewhere dark where the Milky Way stretches across your sky like a river of light. Wherever you are, whatever time zone cradles you tonight, we're all under the same vast cosmos, all part of the same incredible story I'm about to share with you. And if this journey through space helps you drift off to peaceful sleep while pondering the mysteries of the universe, please consider subscribing to hear more of these cosmic bedtime stories. Hit that like button if you find wonder in the darkness between stars, because tonight we're going to explore something that might change how you think about our place in the universe. It's a question that might seem impossible at first, perhaps even absurd to consider, but bear with me as we explore this gentle mystery together. What if I told you that in 2019, while you were going about your daily life, while you were sleeping, working, loving, living, something ancient and extraordinary passed through our solar system? Not just passed through, but announced itself to us in a way that we've only witnessed once before in all of human history. This visitor came from beyond our sun's influence, from the vast darkness between stars, carrying with it secrets from another part of our galaxy, perhaps even memories of an alien sun that died before our Earth was born. The visitor's name was Borisov, and yes, I know that's not the most poetic name for something so extraordinary, but sometimes the universe's greatest mysteries come with simple labels that barely hint at their true significance. The 2I simply means it was the second interstellar object we've ever detected, the second confirmed visitor from beyond our solar system. The Borisov honors Gennady Borisov, an amateur astronomer in Crimea, who first spotted this cosmic wanderer on August 30th, 2019, using a telescope he built himself. Imagine that for a moment. A human being, perhaps not so different from you, looking up at the night sky with an instrument crafted by their own hands and discovering something that had been travelling through space for millions, perhaps billions of years, just to pass by our cosmic neighbourhood at exactly the right moment for human eyes to witness it. But here's where our contemplation begins, where the real mystery starts, to whisper its questions into the cosmic darkness. What if 2I/Borisov wasn't alone? What if this interstellar comet, this frozen wanderer from another star system, was merely one visible member of a vast invisible procession that passes through our solar system constantly? What if we're not experiencing rare, isolated visits from beyond, but rather, we're finally developing the eyes to see what has always been there? A gentle, eternal rain of interstellar objects drifting through our local space like seeds on a cosmic wind. Consider this with me for a moment, and let your mind expand to embrace the vastness of what we're discussing. Our solar system, as enormous as it seems to us, is just a tiny bubble in an ocean of space. The distance from our Sun to Neptune, the edge of our planetary system, is about 2.8 billion miles. That seems impossibly vast, doesn't it? You could fit every planet in our solar system between Earth and our moon with room to spare, and yet Neptune is almost 100 times farther away than that. But even this enormous distance is nothing compared to the space between stars. The nearest star to our Sun, Proxima Centauri, is about 25 trillion miles away. If you compressed the distance from the Sun to Neptune into a single inch, the distance to Proxima Centauri would be about a mile. We exist in an archipelago of stars, islands of light and warmth separated by vast oceans of darkness and cold. And through these cosmic oceans, objects drift. They drift for millions of years, billions of years, carrying the chemistry of their home systems with them like messages in bottles thrown into an infinite sea. 2I/Borisov was one such message that we happened to intercept, to read briefly before it continued on its eternal journey. When astronomers first confirmed its interstellar nature, when they calculated its trajectory and realized it couldn't possibly be bound to our Sun's gravity, there was a moment of profound recognition. We were looking at something genuinely alien, something that had formed around another star, possibly at a time when our Earth was young or perhaps not even formed yet. The comet appeared almost ordinary at first glance, which itself is extraordinary when you think about it. It looked like comets from our own solar system, a fuzzy ball of light with a tail streaming behind it as the Sun's heat vaporized its ancient ices. But the ordinariness was deceptive. This was ice that had never felt our Sun's warmth before. Dust that had condensed around an alien star. Molecules that might have witnessed the birth and death of worlds we'll never know existed. Every particle streaming off Borisov as it approached our Sun was a piece of another solar system, a fragment of foreign chemistry entering our local space for the first time in cosmic history. The observations began immediately. Telescopes around the world and in space turned toward this visitor, gathering every photon of light it reflected, analyzing every wavelength of radiation it emitted. The Hubble Space Telescope captured images of Borisov as it approached the Sun, showing its coma, the glowing envelope of gas surrounding its nucleus, extending for hundreds of thousands of miles. Spectroscopic analysis revealed the presence of water vapor, carbon monoxide and other compounds, but in proportions slightly different from what we typically see in our own comets. It was as if we were reading a recipe from another cosmic kitchen, where the ingredients were the same, but the proportions reflected different conditions, different histories, different stories of formation and evolution. What struck astronomers most profoundly was how Borisov's composition suggested that wherever it came from, the basic chemistry of planet formation might be similar throughout our galaxy. The building blocks of worlds, the raw materials from which planets, and possibly life itself might arise, appear to be universal. This visitor wasn't radically exotic in its composition. It was familiar enough to suggest that the processes that built our solar system might be common throughout the cosmos. And if the processes are common, if the chemistry is similar, then perhaps what emerges from those processes, worlds, oceans, perhaps even life, might not be unique to our small corner of space. But let's return to our central question, the one that transforms Borisov from a singular event into something far more profound. What if it wasn't alone? The mathematics of this possibility are staggering and beautiful. Space is so vast and our ability to detect objects is so limited that we only see the tiniest fraction of what passes through our solar system. Borisov was visible because it was relatively large. Its nucleus was estimated to be about a mile across, and because it developed a bright coma and tail as it approached the Sun. But for every comet like Borisov that announces itself with glowing gases and streaming dust, how many smaller, darker objects slip by unnoticed? Imagine standing in a field during a gentle snowfall at night, with only a small flashlight to illuminate the falling flakes. You'd see the snowflakes that pass through your beam of light, but you'd know that countless others are falling all around you in the darkness. The ones you see aren't special or unique. They're simply the ones that happen to pass through the small volume of space you can observe. Our telescopes are like that flashlight, and objects like Borisov are the snowflakes we happen to catch in our beam. The darkness around us might be full of interstellar wanderers, a constant gentle precipitation of objects from other star systems, and we're only just beginning to develop the ability to see them. The timing of Borisov's discovery is itself a clue to this larger mystery. It arrived just 2 years after Oumuamua, the first confirmed interstellar object, passed through our solar system in 2017. For all of human history, for all the centuries we've been watching the skies with increasing sophistication, we'd never detected a confirmed visitor from another star system. Then suddenly, within 2 years, we found two. The optimistic interpretation, the one that fills me with wonder, is not that interstellar objects suddenly started visiting our solar system in 2017. Instead, perhaps our technology and our systematic surveys of the sky finally reached the threshold where we could detect what had always been there. Think about this from a slightly different angle. Our solar system has been orbiting the center of the Milky Way galaxy for 4.6 billion years. In that time, we've completed about 20 full orbits, passing through different regions of our galaxy, encountering different stellar neighborhoods. Each region of space has its own population of stars, its own collection of planetary systems, its own cloud of ejected comets and asteroids. As we move through these regions, as our solar system travels through space at about 450,000 miles per hour, we're constantly entering new territory, constantly encountering objects that have been ejected from other star systems. The process that sends these objects on their interstellar journeys is happening everywhere, all the time. When planetary systems form, they're messy affairs. Planets migrate, gravitational interactions fling smaller objects in all directions, and some of these objects achieve escape velocity, breaking free from their parent star's gravity to wander the galaxy forever. It's estimated that during the formation of our own solar system, we ejected far more material than we kept. For every asteroid and comet that remains bound to our sun, perhaps hundreds or thousands were flung into interstellar space, beginning their own eternal journeys between the stars. If every star system in our galaxy has undergone similar processes, if every planetary system has ejected swarms of comets and asteroids into interstellar space, then the galaxy must be full of these wanderers. They're the cosmic equivalent of dandelion seeds, blown from their parent systems by gravitational winds, drifting through space until they happen to pass near another star. Most will never encounter another star system closely enough to be captured or even significantly deflected. They'll wander forever in the darkness between stars, carrying their loads of ice and rock and organic molecules through the cosmic void. Borisov's trajectory told us it had been traveling for a very long time. Its path through our solar system was hyperbolic, meaning it was moving too fast for our sun's gravity to capture it. It came from the general direction of the constellation Cassiopeia, though not from any particular star we can identify. This is because over the millions of years of its journey, Both Borisov and the stars themselves have moved significantly. Trying to trace Borisov back to its origin is like trying to determine which tree a particular leaf came from after it's been carried by the wind for miles. The landscape itself has changed during the journey. The speed at which Borisov entered our solar system, about 87,000 miles per hour relative to the Sun, tells us something profound about its journey. This wasn't an object that had been recently ejected from a nearby star. This was something that had been travelling for millions, perhaps hundreds of millions of years. During that time, it would have been slowly altered by its journey through interstellar space. Cosmic rays would have bombarded its surface, creating complex organic molecules in its ice. The gentle pressure of starlight from distant stars would have subtly influenced its path. It might have passed through clouds of interstellar dust and gas, accumulating or losing material along the way. When we observed Borisov, we weren't just seeing a comet. We were seeing a cosmic archaeologist's artifact, an object that had been shaped by its immense journey through space and time. Every feature we observed, its size, its composition, its activity pattern as it approached the Sun, was the result of both its original formation around another star and its subsequent evolution during its interstellar voyage. It was simultaneously ancient and fresh, carrying primordial ices from its formation, while presenting a surface that had been processed by millions of years of cosmic radiation. The way Borisov behaved as it passed through our solar system was remarkably similar to our own comets, and this similarity is perhaps more mysterious than if it had been wildly different. As it approached the Sun, it began to outgas, its ices sublimating directly from solid to gas, creating the characteristic coma and tail that we associate with comets. The rate at which this happened, the way the comet brightened and then faded, the spectrum of light it emitted, all of these were within the range of what we see from comets that formed in our own solar system. It was as if the universe was telling us that the processes that create comets are universal, that the same physics and chemistry operate around other stars as they do around our Sun. But there were subtle differences too, whispers of its alien origin. The ratio of carbon monoxide to water in Borisov's coma was higher than what we typically see in our comets. This might indicate that it formed in a colder region of its parent system, or perhaps around a star that was different from our Sun in some fundamental way. These small differences are like accent marks in a familiar language, hints that while the basic vocabulary of cosmic chemistry might be universal, each star system speaks with its own subtle dialect. As Borisov swung around the Sun and began its journey back into interstellar space, astronomers continued to observe it for as long as possible. They watched as its activity decreased, as its tail faded, as it gradually returned to the frozen, dormant state in which it had spent most of its existence. In April 2020, observations suggested that the comet might have fragmented, possibly due to the stresses of its close approach to the Sun. If true, this means that pieces of Borisov, fragments of another star system, might now be on slightly different trajectories, spreading the material of its parent system even more widely through space. The last observations of Borisov were made in early 2020, as it became too faint for even our most powerful telescopes to detect. It's now continuing its journey through space, heading in the general direction of the constellation Telescopium. Though it won't reach any particular star for millions of years, it will wander through the darkness, slowly cooling, slowly being altered by cosmic rays and the gentle influences of distant stars, until perhaps, in some unimaginably distant future, it might pass through another star system where other observers might wonder about its origin just as we did. But what if Borisov's departure wasn't really a goodbye? What if it was more like watching one car pass on a highway, knowing that more are certainly coming? The statistics suggest that at any given moment there might be thousands, perhaps millions of interstellar objects within the orbit of Neptune. Most are too small to detect, or too dark, or simply too far from the Sun to be visible with our current technology. They're passing through our solar system constantly, these ambassadors from other stars carrying their cargoes of information about distant places and ancient times. Some scientists have suggested that interstellar objects might have played a role in the development of our own solar system. If these objects are as common as we're beginning to suspect, then over the 4.6 billion year history of our solar system, countless numbers of them must have passed through. Some would have been captured by the Sun's gravity, becoming permanent residents. Others might have collided with planets or moons, delivering exotic materials or perhaps even organic molecules from other star systems. In this view, our solar system isn't a closed system that evolved in isolation, but rather an open system that has been exchanging material with the rest of the galaxy throughout its history. This idea transforms our understanding of our cosmic neighborhood. We're not living in a pristine, isolated bubble of space dominated entirely by our Sun's influence. Instead, we're living in a space that's constantly being visited by objects from elsewhere. A cosmic crossroads where material from throughout the galaxy passes by. Most of these visitors are invisible to us, too small or too dark to detect, but they're there nonetheless, silent travelers carrying their ancient secrets through our local space. The discovery of Borisov also raises profound questions about the nature of our observations and what they mean for our understanding of our place in the universe if we've only recently developed the ability to detect these interstellar visitors. What else might be passing through our solar system that we still can't see? What other categories of objects, what other phenomena might be common throughout the galaxy but still invisible to our current technology? Each advancement in our ability to observe the universe has revealed new layers of complexity and wonder. The discovery of interstellar objects might be just the beginning of a new chapter in our understanding of how star systems interact with each other across the vast distances of space. Consider the implications for the spread of life through the galaxy. If objects are constantly being exchanged between star systems, if material from one system can find its way to another, then the building blocks of life, or perhaps even life itself in some dormant form, might be able to travel between stars. This isn't science fiction, it's a serious scientific hypothesis called panspermia. While we have no evidence that Borisov or any other interstellar object has ever carried life, the mere fact that such objects exist and are apparently common makes the possibility more plausible. The galaxy might be more interconnected than we ever imagined, with star systems not as isolated islands but as nodes in a vast network connected by these travelling objects. The space between stars isn't the empty void we once imagined it to be. As we settle deeper into this cosmic contemplation, let your mind drift with me into that darkness between the lights, that vast ocean of space where Borisov spent most of its existence. This isn't a darkness of absence, but a darkness full of potential, crossed by invisible currents and pathways that we're only beginning to understand. Just as ocean currents carry seeds and nutrients across Earth's seas, there might be currents in space, not of water but of gravity, radiation, and stellar winds that guide objects like Borisov on their interstellar journeys. When we look up at the night sky, we see stars as fixed points of light, seemingly motionless in their constellations. But this is an illusion created by our brief human lifespans. In reality, every star is in motion, orbiting the center of our galaxy, moving through space at hundreds of thousands of miles per hour. Our sun and all the stars we see are part of a vast rotating disk of stars, gas and dust that we call the Milky Way. And within this disk, stars don't move in perfect circles. They bob up and down through the galactic plane. They speed up and slow down as they encounter regions of different density. They respond to the gravitational pull of massive stars, star clusters, and clouds of dark matter that we can't even see. These motions create a complex, ever-changing gravitational landscape through which objects like Borisov must navigate. Imagine, if you will, a leaf falling not through still air, but through air full of gentle breezes, updrafts, and eddies. The leaf's path would be complex, influenced by every current of air it encounters. Similarly, an interstellar object's path through space is influenced by every star it passes, even those at great distances. Over millions of years, these gentle influences accumulate, creating paths through space that might be followed by many objects, cosmic highways that connect different regions of our galaxy. The concept of these interstellar highways isn't just theoretical speculation. Astronomers have identified structures in our galaxy called stellar streams, long, thin associations of stars that move together through space. These streams are often the remnants of smaller galaxies or star clusters that have been torn apart by our galaxy's gravity. Their stars spread out along their orbital path like pearls from a broken necklace. If stars can form these streams, these rivers of suns flowing through space, might not smaller objects form similar structures? Might there be streams of comets and asteroids, invisible rivers of ice and rock flowing between the stars? Borisov's path through our solar system offers us a glimpse of these cosmic currents. It approached from a direction that astronomers call the solar apex, the direction our sun is moving through space. This might not be a coincidence. As our solar system plows through space, we're more likely to encounter objects coming from ahead of us, just as a car driving through falling snow encounters more snowflakes on its windshield than on its rear window. Borisov might have been part of a diffuse cloud of objects that our solar system is currently passing through, a cloud so sparse that we only notice the occasional object that passes close enough to the sun to become visible. The velocity of interstellar objects as they pass through our solar system tells us something profound about the dynamics of our galaxy. Objects like Borisov aren't moving at random speeds in random directions. Their velocities cluster around certain values that reflect the average motion of stars in our local region of the galaxy. This is called the local standard of rest, a kind of average velocity for our stellar neighborhood. Objects that have been wandering between stars for millions of years tend to have velocities close to this average, as their interactions with many stars over time have normalized their motion to match the general flow of our local galactic region. Think about what this means for a moment. These interstellar objects aren't wild, chaotic projectiles shooting through space at random. They're more like boats that have been set adrift in a slow-moving river, gradually adjusting their speed to match the current. Over time, through countless gentle gravitational interactions with distant stars, they become synchronized with the general motion of our region of the galaxy. They become part of a vast, slow cosmic circulation system that we're only beginning to perceive. This circulation system might have patterns and structures that we haven't yet recognized. Just as Earth's ocean currents form gyres and streams that persist for thousands of years, the gravitational currents in our galaxy might create persistent paths that interstellar objects tend to follow. Some regions of space might be highways where the density of interstellar objects is higher, while other regions might be relatively empty voids. Our solar system's path through the galaxy would take us through different regions with different densities of these objects, possibly explaining why we might see them in clusters rather than at a steady rate. The idea of clustering is particularly intriguing when we consider the timing of our discoveries. Oumuamua in 2017, Borisov in 2019. Two confirmed interstellar objects within 2 years, after none in all of previous history. While this might simply reflect our improved ability to detect such objects, it might also indicate that we're currently passing through a region of space with a higher density of interstellar wanderers. Perhaps we're crossing one of these cosmic highways right now, and the coming years might bring more discoveries of such objects. These highways wouldn't be straight lines through space, but complex three-dimensional paths that wind through our galaxy's gravitational landscape. They would be influenced by the massive molecular clouds where stars are born, by the spiral arms of our galaxy where star density is higher, by the gravitational wake of massive stars as they plough through space. An object following one of these paths might take a circuitous route through the galaxy, like a river winding through a landscape, following the path of least resistance through the gravitational terrain. The chemistry that Borisov carried with it provides clues about these cosmic pathways. The high ratio of carbon monoxide to water in its composition suggests it formed in a cold region, possibly in the outer reaches of its parent star system. But it also tells us that wherever it formed, the basic ingredients were similar to what we find in our own solar system. Carbon, oxygen, hydrogen, the elements that make up most of Borisov's ice, are among the most common elements in the universe. They're created in stars and distributed through space when those stars die, enriching the interstellar medium with the raw materials for new stars, planets, and comets. This cosmic recycling system means that the highways between stars aren't just carrying objects, they're carrying the processed materials of stellar evolution. Every comet like Borisov is a sample of the conditions in another star system, a frozen record of the chemistry and physics that operated there. As these objects travel between stars, they're potentially spreading this material throughout the galaxy, creating a slow mixing of chemical ingredients across vast distances and timescales. The radiation environment of interstellar space also plays a role in shaping these cosmic highways. Between the stars, objects are bombarded by cosmic rays, high-energy particles accelerated by supernovae and other violent events. This radiation can alter the chemistry of interstellar objects, creating complex organic molecules in their ice, breaking down simple molecules into reactive fragments that can recombine in unexpected ways. By the time an object like Borisov reaches our solar system, it's been chemically processed by millions of years of radiation exposure, transformed into something that might be quite different from what originally left its parent system. The magnetic fields that permeate our galaxy add another layer of complexity to these interstellar paths. While magnetic fields don't directly affect the motion of objects like Borisov, They do influence the charged particles of the stellar wind and cosmic rays that bombard these objects. They create regions of space where radiation is more or less intense, potentially affecting the rate at which interstellar objects are processed during their journeys. These magnetic fields wind through our galaxy like invisible rivers, creating a complex topology that might influence where and how interstellar objects travel. As our technology improves, we're beginning to map these invisible structures in our galaxy. Radio telescopes detect the emission from hydrogen gas that fills the space between stars. Infrared telescopes peer through the dust that obscures our view of distant regions. X-ray and gamma-ray telescopes detect the high-energy radiation from stellar explosions and other violent events. Each type of observation reveals different aspects of the interstellar medium, gradually building up a picture of the complex environment through which objects like Borisov must travel. One of the most fascinating aspects of these cosmic highways is their potential role in connecting different epochs of our galaxy's history. An object ejected from a star system billions of years ago might still be traveling through space today, carrying information about conditions in our galaxy's past. Borisov might have formed when our galaxy was younger, when the rate of star formation was higher, when the chemistry of the interstellar medium was subtly different. In this sense, interstellar objects are time capsules, preserving information about different eras of galactic evolution. The gravitational influence of our galaxy's dark matter also shapes these cosmic highways in ways we don't fully understand. Dark matter, which makes up most of our galaxy's mass but doesn't interact with light, creates a gravitational scaffold that influences the motion of everything else. Streams of dark matter might create preferred paths through space, channels where the combined gravitational effect of visible and dark matter creates corridors that interstellar objects tend to follow. We can't see these dark matter structures directly, but we might be able to infer their existence from the patterns of interstellar objects that pass through our solar system. Consider the possibility that Borisov's path through our solar system was not random, but was guided by these large-scale structures in our galaxy. Its trajectory might have been shaped by encounters with giant molecular clouds millions of years ago, deflected by the gravitational wake of massive stars, channeled by the density waves that create our galaxy's spiral arms. By the time it reached us, its path was the result of countless subtle influences accumulated over cosmic time, a trajectory that tells the story of its journey through our galaxy's complex gravitational landscape. The seasonal patterns of our solar system's motion through space add another dimension to this cosmic highway system. As our sun orbits the galactic center, it also oscillates up and down through the galactic disk, like a horse on a carousel that also moves up and down. This oscillation has a period of about 70 million years, taking us through regions of different density and different populations of stars. When we're passing through the denser regions of the galactic disk, we might encounter more interstellar objects. When we're in the less dense regions above or below the disk, encounters might be rarer. Right now, our solar system is moving upward through the galactic disk, having crossed the midplane relatively recently in cosmic terms. This motion affects not just our likelihood of encountering interstellar objects, but also the directions from which they're likely to approach. As we move through different regions of the galaxy, the apparent source direction of interstellar objects would shift, creating patterns that future observations might reveal. If we observe enough interstellar objects over the coming decades, we might be able to map the local structure of these cosmic highways, understanding how material flows through our region of the galaxy. The possibility that our solar system is currently near or crossing one of these cosmic highways is tantalizing. If true, it would mean that the discoveries of Oumuamua and Borisov are just the beginning. We might be entering a period where interstellar objects are more common, where we have the opportunity to study multiple visitors from other star systems. Each one would provide new information about the conditions in other parts of our galaxy, new clues about how planetary systems form and evolve, new pieces of the puzzle of our cosmic environment. These highways might also vary in their composition. Some might carry predominantly icy objects like Borisov, formed in the outer regions of their parent systems. Others might carry rocky objects, asteroids ejected from the inner regions of other star systems. Still others might carry objects we haven't even imagined yet, perhaps aggregates of dark matter, or objects formed in environments very different from our solar system. The diversity of what travels these cosmic highways might surprise us as our ability to detect and study such objects improves. The interaction between these cosmic highways and our solar system's own cloud of comets adds another layer of complexity. Our solar system is surrounded by the Oort cloud, a vast sphere of icy objects extending perhaps halfway to the nearest star. As interstellar objects pass through this cloud, they might gravitationally perturb our own comets, sending some inward toward the Sun while capturing others into new orbits. This exchange means that our solar system isn't just a passive observer of these cosmic highways, but an active participant, contributing our own objects to the interstellar flow, while occasionally capturing visitors from elsewhere. Some scientists have suggested that this exchange might be more common than we realize. Over the billions of years of our solar system's existence, we might have captured many interstellar objects, which now masquerade as long-period comets in our Oort cloud. Similarly, many objects that we think of as native to our solar system might have been ejected long ago and are now traveling the cosmic highways, carrying information about our Sun and planets to distant regions of the galaxy. In this view, star systems throughout the galaxy are constantly exchanging material, creating a slow mixing that connects all parts of our galaxy across vast scales of space and time. Before Borisov graced our solar system with its presence, there was another visitor, one that challenged our understanding and sparked our imagination in ways that still resonate through the scientific community. Oumuamua, discovered on October 19th, 2017, was humanity's first confirmed glimpse of an object from another star system, and what a peculiar glimpse it was. Unlike Borisov, which announced itself with a familiar cometary appearance, Oumuamua was something altogether different, something that made us question our assumptions about what interstellar visitors should look like. The name Oumuamua comes from Hawaiian, meaning roughly scout, or messenger from afar arriving first, a fitting name for this pioneering object that opened our eyes to the reality of interstellar visitors. It was discovered by the Pan-STARRS telescope in Hawaii, part of a systematic survey designed to detect potentially hazardous asteroids. But Oumuamua was no ordinary asteroid. Its trajectory immediately marked it as something special. Its path through our solar system was hyperbolic, moving too fast to be bound by our Sun's gravity, confirming its interstellar origin. What made Oumuamua truly extraordinary wasn't just its interstellar nature, but its properties. As astronomers rushed to observe this unique object before it faded from view, they discovered something unexpected. Oumuamua was tumbling through space, rotating every 7.3 hours, and its brightness varied dramatically during this rotation. This variation suggested that Oumuamua was highly elongated, perhaps 10 times longer than it was wide, a shape unlike anything we'd seen in our own solar system. Imagine a cosmic cigar or perhaps a flattened disk spinning through space, reflecting sunlight differently as it tumbled, creating a lighthouse effect that announced its unusual form. The absence of a visible coma or tail, despite passing relatively close to the Sun, suggested that Oumuamua was not an icy comet like Borisov, but something else, perhaps a rocky asteroid, or something even more exotic. Its surface appeared to be reddish, similar to some objects in the outer regions of our solar system, possibly indicating organic compounds that had been irradiated over millions of years of cosmic ray exposure. But the most puzzling observation came as Oumuamua left our solar system. It showed a small but measurable acceleration that couldn't be explained by gravity alone. This unexpected acceleration sparked intense debate and speculation. In our solar system, such acceleration in comets is caused by outgassing, ice turning to vapor and creating a jet effect. But Oumuamua showed no visible signs of outgassing, no coma, no tail, nothing that would indicate the presence of volatile ices. Some scientists proposed that it might be composed of molecular hydrogen ice, which would be invisible to our telescopes as it sublimated. Others suggested it might be a dust bunny, a loosely bound collection of dust particles light enough to be pushed by radiation pressure. And yes, some even speculated, though most scientists remained skeptical, that it might be artificial, a piece of alien technology sailing on the light of stars. The timing of Oumuamua's discovery, just 2 years before Borisov, raises profound questions about the frequency of such encounters. For all of human history, we had never detected an interstellar object passing through our solar system. Then, within a span of just 2 years, we found 2. This clustering might be telling us something important about either our detection capabilities or the actual distribution of interstellar objects in space. Perhaps we've finally reached a threshold in our surveillance of the sky where we can detect these fleeting visitors. Or perhaps we're passing through a region of space where such objects are more common, a cosmic highway intersection where paths from multiple star systems converge. The differences between Oumuamua and Borisov are as instructive as their similarities. While Borisov looked and behaved much like comets from our own solar system, Oumuamua was unlike anything in our cosmic catalogue. This diversity suggests that the population of interstellar objects might be far more varied than we imagined. Each star system, with its unique conditions and history, might produce different types of objects, different compositions, different shapes. The galaxy might be full of cosmic variety, each object carrying the signature of its unique origin. Consider what this means for our understanding of planetary system formation. If Oumuamua and Borisov represent just 2 samples from a vast population of interstellar objects, and they're already this different from each other, what else might be out there? Perhaps there are interstellar objects made of materials we've never encountered, formed under conditions we haven't imagined, shaped by processes we don't yet understand. Each new discovery might challenge our theories about how planets and smaller bodies form, forcing us to expand our models to accommodate the diversity of the cosmos. The trajectory analysis of both objects provides clues about their origins, though the specific star systems they came from remain unknown. Oumuamua appeared to come from the direction of the constellation Lyra, roughly where the bright star Vega is located, though it didn't actually come from Vega itself. Its incoming velocity relative to the local standard of rest was surprisingly close to zero, which some astronomers find puzzling. It's as if Oumuamua was at rest relative to the average motion of stars in our neighbourhood, and we ran into it rather than it running into us. This could mean it's been floating in interstellar space for a very long time, long enough for its motion to be averaged out by countless distant gravitational interactions. Borisov, on the other hand, came from a different direction entirely, from the constellation Cassiopeia, and with a different velocity profile. This diversity in approach directions and velocities tells us that interstellar objects aren't all coming from the same source or following the same paths. They're approaching our solar system from all directions, a three-dimensional rain of cosmic wanderers, each with its own history and trajectory. We're not seeing a stream from a particular source, but rather a sampling of objects from throughout our galactic neighbourhood. The challenge of studying these objects is immense. They appear without warning, often discovered only when they're already close to their nearest approach to the Sun. We have just weeks or months to observe them before they fade from view, racing away into the darkness from which they came. With Oumuamua, we had even less time because it was discovered after its closest approach to the Sun, when it was already on its way out of our solar system. Every observation had to be rushed. Every telescope that could be pointed at it was mobilized, and still we were left with more questions than answers. This race against time highlights the need for better detection systems and rapid response protocols. Several new telescopes and surveys are coming online that should dramatically improve our ability to detect interstellar objects. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will survey the entire visible sky every few nights, potentially discovering many more interstellar visitors. When it becomes fully operational, we might find that objects like Oumuamua and Borisov aren't rare at all, but rather common visitors that we've simply been unable to detect until now. The scientific community's response to these discoveries has been remarkable. Papers have been published exploring every aspect of these objects, from their possible origins to their implications for planetary formation theories. Some scientists have proposed missions to intercept future interstellar objects, to study them up close, or even return samples to Earth. While such missions would be technically challenging, requiring rapid response and high-velocity spacecraft, they're not impossible with near-future technology. Imagine being able to hold in our hands a piece of another star system, to analyze in our laboratories material that formed around an alien sun. The possibility that we've been missing interstellar objects all along is both humbling and exciting. How many Oumuamuas and Borisovs have passed through our solar system while humans looked up at the night sky, unaware of these cosmic visitors? During the age of dinosaurs, during the formation of Earth's first oceans, during the birth of our solar system itself, interstellar objects have likely been passing through, silent and unnoticed, carrying their secrets through our local space. We're like people who have lived by the ocean all their lives but have only just invented the telescope to see the ships passing on the horizon. The implications extend beyond just the objects themselves. If interstellar objects are common, they might have played a role in the evolution of our solar system and others. They could deliver exotic materials, trigger comet showers by gravitationally perturbing the Oort cloud, or even deliver the building blocks of life between star systems. Each object is a potential messenger, carrying information and possibly material that could influence the development of planetary systems. The story of our solar system might be incomplete without considering the role of these interstellar wanderers. The debate over Oumuamua's nature continues to this day, with new papers and theories regularly appearing in scientific journals. Some researchers have suggested it might be a fragment of a planet destroyed by tidal forces near its parent star, explaining its unusual shape and composition. Others propose it could be a chunk of solid nitrogen, like the surface of Pluto, which would explain its acceleration without visible outgassing. Still others maintain that we simply don't have enough data to determine its true nature, that Oumuamua will remain a mystery, a reminder of how much we still don't know about our cosmic environment. This uncertainty is perhaps Oumuamua's greatest gift to science. It reminds us that the universe is still full of surprises, that our models and theories are incomplete, that there's so much more to discover. Every assumption we make about how planetary systems work, about what kinds of objects exist in space, needs to be tested against the reality of what we observe. Oumuamua challenged those assumptions, showing us something we didn't expect, forcing us to expand our thinking about what's possible. The relationship between Oumuamua and Borisov, the first two confirmed interstellar objects, is like the relationship between the first two exoplanets discovered orbiting other stars. They showed us that what we're seeing isn't unique or exceptional, but rather the tip of an iceberg, the first glimpses of a vast population waiting to be discovered. Just as we now know of thousands of exoplanets with properties ranging from familiar to bizarre, we might soon catalogue hundreds or thousands of interstellar objects, each one teaching us something new about our galaxy. The echo of Oumuamua's passage through our solar system continues to reverberate through our understanding of our cosmic neighbourhood. It transformed interstellar objects from theoretical possibilities to observed realities. It showed us that we're not isolated in our solar system but are constantly being visited by objects from elsewhere. It reminded us that the galaxy is more dynamic and interconnected than we imagined. And perhaps most importantly, it prepared us to better understand and appreciate Borisov when it arrived 2 years later. When Borisov was discovered, astronomers were ready. The lessons learned from Oumuamua had been absorbed, the observation protocols refined, the theoretical frameworks expanded. We knew to look for unusual accelerations, to quickly measure compositions, to track the object for as long as possible. The discovery of Borisov validated some of our ideas about interstellar objects while challenging others. Its cometary nature showed that not all interstellar objects are like Oumuamua, that there's a diversity in this population that we're only beginning to appreciate. Together, Oumuamua and Borisov have opened a new chapter in astronomy, the study of interstellar objects. They've shown us that our solar system is not a closed box but an open system, constantly exchanging material with the rest of the galaxy. They've given us our first direct samples, albeit observed from a distance, of material from other star systems. They've challenged our theories and expanded our horizons, showing us that the universe is more connected and more diverse than we knew. Chapter 4. The Invisible Companions. For every Borisov that blazes across our telescopes with its glowing coma, for every Oumuamua that tumbles through our solar system, just bright enough to detect, How many others pass by unseen in the darkness? This question haunts astronomers and fills the imagination with possibilities. We're like ancient mariners who can only see the tips of icebergs above the water, knowing that beneath the surface lies far more than we can observe. The invisible population of interstellar objects might outnumber the visible ones by factors of thousands, millions, or even more. Let's contemplate the mathematics of invisibility for a moment. Our ability to detect objects in space depends on several factors: their size, their distance from us, their distance from the sun, and their surface properties. An object needs to reflect enough sunlight to be visible to our telescopes, and that reflected light decreases with the square of the distance. Double the distance, and an object becomes 4 times fainter. Triple it, and it becomes 9 times fainter. This cruel arithmetic means that even our most powerful telescopes can only see relatively large, relatively close objects. Borisov was detected because it was about a mile across and developed a bright coma as it approached the sun. But what about smaller objects? What about those the size of buildings, cars, or even smaller? These objects would be completely invisible to our current technology unless they passed extremely close to Earth, and even then we might miss them. The galaxy could be full of small interstellar objects, a cosmic hail of pebbles and boulders from other star systems, and we would never know they were there. Consider the size distribution of objects in our own solar system. For every large asteroid, there are hundreds of smaller ones. For every small asteroid, there are thousands of tiny meteoroids. This pattern, where smaller objects vastly outnumber larger ones, is likely universal. If it applies to interstellar objects as well, then for every Borisov-sized comet passing through our solar system, there might be millions of smaller fragments, invisible to our telescopes but still carrying their cargo of information from other star systems. The composition of these objects also affects their visibility. Borisov was visible largely because it was made of ice that sublimated as it approached the sun, creating a bright cloud of gas and dust. But what about objects made of dark, non-reflective materials? What about chunks of carbon-rich rock, or objects covered in organic polymers that absorb rather than reflect light? These dark objects could pass much closer to us than Borisov did, and still remain invisible, ghost ships sailing through our solar system without leaving a trace we can detect. The timing of our observations matters too. We can only detect objects when we're looking in the right direction at the right time with the right instruments. Space is vast, and our telescopes can only survey a small fraction of it at any given moment. An interstellar object might pass through our solar system when all our telescopes are pointed elsewhere, or when the object is in the daylight sky where ground-based telescopes can't observe, or when it's hidden behind the sun from Earth's perspective. For every object we detect, how many do we miss simply because we weren't looking in the right place at the right time? The speed of these objects compounds the challenge. Interstellar objects typically pass through our solar system at speeds of tens of thousands of miles per hour. They don't linger. They race through like cosmic bullets, spending only months or years within the orbit of Neptune. An object might enter our solar system, swing around the sun, and exit back into interstellar space all within a single Earth year. If we don't catch it during that brief window, it's gone forever, continuing its eternal journey through the galaxy. Current estimates based on the detection of Oumuamua and Borisov and our understanding of our detection capabilities suggest that there might be thousands or even millions of interstellar objects within our solar system at any given time. Most are too small or too distant to detect. They're distributed throughout the vast volume of our solar system, from the inner planets to the distant Kuiper belt and beyond. We're surrounded by an invisible population of cosmic wanderers, each one a messenger from another star system that we'll never be able to read. Some of these invisible companions might be quite exotic. In the vast diversity of planetary systems in our galaxy, conditions exist that are very different from those in our solar system. Some stars are much hotter than our Sun, others much cooler. Some planetary systems might form in regions of space rich in heavy elements, others in regions that are metal poor. These different conditions would produce different types of objects, with compositions and properties we might not expect. Imagine objects made primarily of iron, forged in the cores of planets that were subsequently destroyed, or objects made of pure carbon, diamonds the size of mountains tumbling through interstellar space, or objects composed of materials that don't naturally occur in our solar system. Exotic ices formed under pressures and temperatures we've never observed. Each of these objects would have different reflective properties, different thermal characteristics, different visibilities to our telescopes. Some might be easier to detect than we expect. Others might be nearly impossible to see even if they passed close to Earth. The thermal properties of these objects add another dimension to their invisibility. Objects in space don't just reflect visible light. They also emit infrared radiation based on their temperature. An object that's been traveling through interstellar space for millions of years would be extremely cold, just a few degrees above absolute zero. As it enters our solar system and is warmed by the sun, it would start to emit more infrared radiation. But this warming takes time, and by the time an object is warm enough to be easily detected in infrared, it might already be on its way back out of our solar system. Some interstellar objects might be in our solar system for extended periods without us knowing. If an object approaches our solar system at just the right angle and speed, it might be captured into a long elliptical orbit around the Sun. These captured objects would become permanent or semi-permanent residents of our solar system, masquerading as long-period comets or distant asteroids. We might have been observing captured interstellar objects for decades without realizing their true nature, assuming they were native to our solar system when they were actually immigrants from other stars. The search for these hidden interstellar residents is ongoing. Astronomers are re-examining the orbits of known comets and asteroids, looking for objects with unusual characteristics that might indicate an interstellar origin. Some objects in our solar system have retrograde orbits, moving in the opposite direction to the planets, which might indicate they were captured from interstellar space. Others have compositions that don't quite match what we expect for objects formed in our solar system. Each of these anomalous objects might be a captured interstellar wanderer, a permanent reminder of our solar system's interaction with the broader galaxy. The technology to detect these invisible companions is improving rapidly. New telescopes with larger mirrors and more sensitive detectors are coming online. Advanced software algorithms can sift through vast amounts of data, identifying moving objects that human observers might miss. Space-based telescopes operating in infrared can detect the heat signatures of objects invisible in visible light. Radio telescopes might detect emissions from certain types of objects. Each new technology opens another window through which we can search for these cosmic visitors. Future missions might be specifically designed to detect and study interstellar objects. Proposals include spacecraft stationed at the gravitational balance points between Earth and the Sun, where they would have a stable vantage point to watch for incoming objects. Others suggest constellations of small satellites spread throughout the inner solar system, creating a detection network that could spot objects from multiple angles. Some visionaries even propose interceptor spacecraft, ready to launch on short notice to rendezvous with newly discovered interstellar objects. The implications of this invisible population are profound. If our solar system is constantly being traversed by objects from other star systems, then the exchange of material between stars might be far more common than we thought. Over the 4.6 billion year history of our solar system, millions or billions of interstellar objects might have passed through. Some would have collided with planets or moons, delivering exotic materials or perhaps even organic molecules. Others might have been captured, becoming permanent parts of our solar system. This invisible traffic might have influenced the evolution of our solar system in ways we don't yet understand. Gravitational perturbations from passing interstellar objects might have affected the orbits of planets or asteroids. Collisions with interstellar objects might have contributed to the late heavy bombardment, a period about 4 billion years ago when the inner planets were pelted with impacts. The delivery of water and organic molecules by interstellar objects might have played a role in making Earth habitable, or even in the origin of life itself. The invisible companions also raise questions about what we're sending out into the galaxy. Just as other star systems are sending objects our way, our solar system has undoubtedly ejected countless objects into interstellar space. Every gravitational interaction between planets and smaller bodies has the potential to fling objects out of our solar system. Over billions of years, we've probably sent millions of comets and asteroids on interstellar journeys. Right now, objects that formed in our solar system might be passing through other star systems, invisible to alien astronomers just as their objects are invisible to us. Some of our invisible companions might be truly ancient, older than our solar system itself. Objects ejected from the first generation of stars in our galaxy, billions of years before our sun formed, might still be wandering through space. These ancient wanderers would carry information about the early galaxy, about conditions that no longer exist, about the first planetary systems to form after the Big Bang. They would be cosmic fossils preserved in the cold of interstellar space, waiting to be discovered and studied. The distribution of these invisible objects might not be uniform. There might be streams or clusters of objects moving together through space, ejected from the same star system or shaped by the same gravitational influences. Our solar system might periodically pass through these denser regions, experiencing showers of interstellar objects like meteor showers but on a much larger scale. These events might leave traces in our geological record, layers of unusual isotopes or minerals that mark times when Earth was peppered with material from other star systems. The challenge of detecting these invisible companions drives innovation in astronomy. New techniques are being developed to find faint, fast-moving objects. Machine learning algorithms are being trained to recognize the subtle signatures of interstellar objects in telescope data. Amateur astronomers with small telescopes are joining the search, knowing that the next interstellar object might be discovered by anyone looking in the right place at the right time. The psychological impact of knowing we're surrounded by invisible visitors from other stars is profound. It changes our perception of our solar system from an isolated island to a busy cosmic crossroads. We're not alone in our corner of space. We're constantly being visited by objects from throughout the galaxy. Most of these visitors pass by unseen and unknown, but they're there nonetheless, silent testimony to the interconnectedness of our galaxy. Every interstellar object that passes through our solar system is more than just a wandering piece of rock or ice. It's a message from another star system, written in the language of chemistry and physics, waiting to be decoded. When we observed Borisov's spectrum, when we analysed the light reflecting off Oumuamua, we were reading these messages, glimpsing the conditions that existed around other stars, perhaps billions of years ago. These objects are libraries of information, archives of cosmic history, carrying stories that span distances and timescales beyond human comprehension. The chemistry of an interstellar object tells us about its birthplace. Every star system has its own chemical fingerprint, determined by the composition of the gas cloud from which it formed, and the nuclear processes that have occurred within its stars. When a comet like Borisov forms in the outer reaches of a planetary system, it incorporates the local chemistry into its ice and dust. The ratios of different isotopes, the presence or absence of certain molecules, the crystalline structure of its ice, all of these preserve information about the conditions during its formation. Borisov's high ratio of carbon monoxide to water, for instance, tells us it likely formed in a cold region, perhaps colder than the regions where most comets in our solar system formed. This simple observation opens a window into the architecture of another planetary system. It suggests that Borisov's parent system might have been different from ours, perhaps with a more massive star that cleared its inner regions more efficiently, or a less massive star that couldn't warm its outer regions as much as our Sun does, or simply a different distribution of temperatures and materials during planet formation. But the messages carried by interstellar objects go beyond their original composition. During their millions of years journeying through interstellar space, these objects are continuously modified by their environment. Cosmic rays bombard their surfaces, breaking molecular bonds and creating new compounds. The constant rain of high-energy particles can transform simple molecules into complex organic compounds, creating a rich chemistry that didn't exist when the object first formed. By the time an interstellar object reaches us, it carries both the story of its birth and the story of its journey. This cosmic ray processing is particularly intriguing when we consider its implications for organic chemistry. Laboratory experiments have shown that when simple ices containing water, methane, ammonia, and other common molecules are exposed to radiation similar to cosmic rays, they can form amino acids, the building blocks of proteins. They can form nucleotide bases, the letters of the genetic alphabet. They can form sugars and lipids, and all manner of complex organic molecules. Every interstellar object is potentially a traveling chemistry laboratory, where these reactions have been occurring for millions of years. Imagine the surface of Borisov or any interstellar comet as a vast chemical workshop. In the outer layers, cosmic rays are constantly creating reactive molecules, radicals and ions that would immediately react if they weren't frozen in place. Deeper inside, protected from the harshest radiation, more stable molecules accumulate. Different depths preserve different epochs of chemistry, like tree rings recording years of growth. When such an object approaches a star and begins to warm, these frozen chemicals suddenly become mobile, reacting with each other in a burst of chemical activity that might create even more complex molecules. the potential for interstellar objects to carry prebiotic molecules, the chemical precursors to life, transforms them from mere curiosities into potentially crucial players in the story of life in the universe. If these objects are common, if they regularly pass through planetary systems, then they might be delivering organic molecules throughout the galaxy. A young planet still cooling from its formation might be seeded with complex organics delivered by passing interstellar comets. The building blocks of life might be distributed throughout the galaxy by these cosmic wanderers, ensuring that wherever conditions are right, life has the raw materials it needs to begin. This isn't just speculation. We know that comets in our own solar system carry complex organic molecules. The Rosetta mission to Comet 67P, Churyumov-Gerasimenko, detected glycine, an amino acid, in the comet's coma. The Stardust mission returned samples from Comet Wild 2 that contained a variety of organic compounds. If our local comets carry such molecules, why wouldn't interstellar comets? And if they do, they might be spreading these molecules across vast distances, potentially seeding life throughout the galaxy. The mineralogy of interstellar objects provides another set of messages. The types of minerals present, their crystal structures, their isotopic compositions, all of these tell stories about temperature, pressure, and chemical conditions during formation. Some minerals only form under specific conditions, acting as thermometers and barometers that record the environment of their creation. Others might preserve magnetic fields, tiny compass needles frozen in stone that point back to the magnetic environment of another star system. Oumuamua's reddish color, for instance, might indicate the presence of organic polymers on its surface, created by billions of years of cosmic ray exposure. These polymers, called tholins, are common on objects in the outer solar system and give them their characteristic red-brown color. But the specific shade, the exact spectral signature, might be different for tholins created in interstellar space versus those created in our solar system. These subtle differences are messages about the radiation environment, the temperature history, the chemical evolution of the object during its long journey. The physical structure of interstellar objects also carries information. Oumuamua's unusual elongated shape, if real, and not an artifact of our limited observations, tells us something about how it formed or how it was modified during its journey. Perhaps it's a fragment of a larger body, broken apart by tidal forces or collisions. Perhaps it formed elongated due to unusual conditions in its parent system, or perhaps its shape was sculpted by billions of years of erosion in interstellar space, where tiny dust grains traveling at high speeds slowly carved away its surface like cosmic sandblasting. The porosity and density of these objects encode information about their formation and evolution. A loosely packed rubble pile structure would indicate gentle accretion in a protoplanetary disk, while a solid monolithic structure might suggest formation under higher pressures or temperatures. The presence or absence of internal voids, the arrangement of different materials, the boundaries between different regions, all of these structural features are messages about the object's history. When an interstellar object begins to outgaze as it approaches a star, the sequence and composition of the released gases provide a kind of chemical stratigraphy. The first gases to escape come from the most volatile, most easily sublimated ices. As the object warms further, progressively less volatile materials begin to escape. This sequence is like reading pages of a book in order, each one revealing information about different components of the object, and therefore different aspects of its formation and evolution. The isotopic ratios in interstellar objects are particularly valuable messages. Different isotopes of the same element have slightly different properties, and their ratios can tell us about the nuclear processes that created them. For instance, the ratio of deuterium to hydrogen and water ice can indicate the temperature at which the ice formed. The ratios of oxygen isotopes can tell us about the stellar processes that created the oxygen. The presence of short-lived radioactive isotopes, if detected, could tell us about recent exposure to supernovae or other high-energy events. These isotopic messages might help us understand galactic chemical evolution. Our galaxy has been chemically enriched over billions of years as successive generations of stars have created heavier elements and distributed them through space. An interstellar object that formed billions of years ago would carry isotopic ratios from that earlier epoch, preserving a record of what our galaxy's chemistry was like in the past. By studying objects of different ages from different regions of the galaxy, we might be able to piece together how our galaxy's chemistry has evolved over cosmic time. The magnetic properties of interstellar objects might preserve information about the magnetic fields in their parent systems. Some minerals can record the strength and direction of magnetic fields present during their formation, acting like billions of tiny compass needles frozen in stone. If we could measure these magnetic signatures in interstellar objects, we might learn about the magnetic environments around other stars, information that would be nearly impossible to obtain any other way. The surface features of interstellar objects, could we observe them in detail, would tell stories of their journey through space. Impact craters from collisions with interstellar dust grains, erosion patterns from particle radiation, deposits of material collected during passage through interstellar clouds. Each feature would be a chapter in the object's travelogue. The accumulation of interstellar dust on an object's surface might even tell us about the composition of the interstellar medium in different regions of the galaxy. Some interstellar objects might carry more exotic messages. If an object passed close to a neutron star or black hole during its journey, it might bear the scars of that encounter. Unusual isotopic ratios created by intense radiation, structural deformation from tidal forces, or a coating of exotic particles. If an object passed through a supernova remnant, it might carry supernova-produced isotopes that would mark the time and place of that passage. These objects would be messengers not just from other star systems, but from some of the most extreme environments in our galaxy. The biological implications of these chemical messages are profound. If interstellar objects can carry complex organic molecules, and if they regularly impact planets and moons, then they might play a role in the origin and distribution of life throughout the galaxy. This process, called lithopanspermia, suggests that life might not arise independently on each habitable world, but might spread from world to world, carried by these cosmic messengers. An impact on a life-bearing world might eject rocks carrying microorganisms into space, where some might eventually be captured by passing interstellar objects and carried to other star systems. While this might sound like science fiction, we know that rocks can be transferred between planets in our own solar system. We have meteorites from Mars and the Moon that were blasted off those worlds by impacts and eventually fell to Earth. Some of these rocks spent very little time in space and arrived at Earth with their interiors still cool, potentially preserving any microorganisms that might have been present. If this can happen within our solar system, why not between star systems, with interstellar objects serving as the carriers? The messages written in ice and stone extend beyond chemistry and biology to fundamental physics. The way interstellar objects interact with our sun's gravity and radiation tells us about their mass, density, and surface properties. Unexpected accelerations, like what was observed with Oumuamua, might reveal new physics or new types of materials. Each object is an experiment in celestial mechanics, testing our understanding of how objects move through space and respond to various forces. Scientists estimate that at this very moment, as you listen to these words, as you perhaps drift towards sleep, millions of interstellar objects might inhabit our solar system. They hide in the darkness between planets, too small or too distant for our instruments to find, like trying to count snowflakes in a blizzard while standing in one small spot with only a candle for light. Borisov was just the one that happened to pass close enough to the sun, large enough to develop a visible coma, bright enough for our telescopes to detect, at just the right time when we were looking in the right direction. In the vastness of space, we're surrounded by invisible visitors we'll never meet, a silent population of cosmic wanderers that vastly outnumbers anything we can observe. The mathematics of this invisible population are both simple and staggering. Consider the volume of space within Neptune's orbit, a sphere roughly 60 astronomical units across, where one astronomical unit is the distance from Earth to the Sun. This volume is approximately 900,000 cubic astronomical units, a space so vast that you could fit every planet in our solar system inside it, thousands of times over with room to spare. Now imagine trying to find objects perhaps only meters or kilometers across in this enormous volume. It's not just looking for a needle in a haystack. It's looking for a particular grain of sand in all the beaches of Earth, while blindfolded at night, with most of the beaches hidden from view. Our current detection capabilities are humbling when considered against this scale. Even our most powerful telescopes can only detect relatively large objects when they're relatively close to the Sun and to Earth. An object needs to reflect enough sunlight for us to see it, and that reflected light follows the unforgiving inverse square law. Double the distance, and an object becomes 4 times fainter. A kilometer-sized object at Jupiter's distance might be visible to our best telescopes, but the same object at Neptune's distance would be completely invisible. And this assumes the object has a relatively reflective surface. A dark, carbon-rich object might be invisible even at much closer distances. The size distribution of objects in space follows what astronomers call a power law. For every large object, there are many more small ones. In our own asteroid belt, for every asteroid larger than 100 kilometers across, there are hundreds larger than 10 kilometers, thousands larger than 100 kilometers 1 kilometer, and millions larger than 100 meters. If this same distribution applies to interstellar objects, and there's no reason to think it wouldn't, then for every Borisov-sized object we detect, there might be millions of smaller ones passing through our solar system completely unnoticed. Let's contemplate what this means in practical terms. Based on the detection of Oumuamua and Borisov, and accounting for our limited detection capabilities, astronomers estimate that the density of interstellar objects in space might be around 0.1 to 1 per cubic astronomical unit for objects larger than 100 meters. This might not sound like much, but when you multiply it by the enormous volume of our solar system, you get millions of objects. And this is just for objects larger than 100 meters. Include smaller objects, and the number grows exponentially. These estimates are uncertain, of course, based on just 2 confirmed detections and numerous assumptions about what we're not seeing. The true number could be much higher or somewhat lower, but even the conservative estimates suggest a hidden population that transforms our understanding of our solar system. We're not living in a pristine bubble of space dominated solely by our sun and its original planets and smaller bodies. We're living in a space that's constantly being traversed by objects from elsewhere, a cosmic intersection where material from throughout the galaxy passes through. The temporal aspect of this cosmic census adds another layer of complexity. Objects don't stay in our solar system. They pass through like ships in the night, spending perhaps a year or 2 within Neptune's orbit before returning to interstellar space. This means the population is constantly changing. The millions of interstellar objects that might be in our solar system today are not the same ones that were here a decade ago, and they won't be the same ones that will be here a decade from now. We're witnessing a constant flow, a river of cosmic material flowing through our local space. This flow isn't uniform in time or space. Our solar system's motion through the galaxy means we're constantly entering new regions of space with potentially different densities of interstellar objects. When we pass through the spiral arms of our galaxy, where star formation is more active and stellar densities are higher, we might encounter more interstellar objects. When we're in the spaces between spiral arms, encounters might be rarer. Our solar system also oscillates up and down through the galactic disk with a period of about 70 million years, taking us through regions of different density and potentially different populations of objects. There might be seasonal variations in the flux of interstellar objects, cosmic weather patterns that we haven't yet recognized. Just as Earth experiences meteor showers when it passes through the debris trails of comets, our solar system might experience showers of interstellar objects when it passes through regions where they're more concentrated. These concentrations might be the result of stellar encounters that ejected swarms of objects, or regions where the galactic gravitational field tends to focus interstellar trajectories, or the remnants of disrupted star systems that scattered their smaller bodies across space. The challenge of conducting this cosmic census with our current technology is like trying to map an entire continent while only being able to see a few meters in any direction. We've developed sophisticated statistical techniques to extrapolate from our limited observations to the broader population, but these techniques rely on assumptions that might or might not be correct. We assume that the objects we can detect are representative of the ones we can't. But what if they're not? What if there's a vast population of objects with properties so different from what we expect that we wouldn't recognize them even if we saw them? Dark objects present a particular challenge for our cosmic census. Most of our detection methods rely on reflected sunlight, but some objects might be so dark that they are essentially invisible even when relatively close. Imagine objects covered in complex organic polymers that absorb rather than reflect light, or objects made of materials that are naturally non-reflective. These dark wanderers could pass through the inner solar system, closer to Earth than Mars, and we might never know they were there. They're the cosmic equivalent of stealth aircraft, invisible to our optical radar. The speed of interstellar objects compounds the detection challenge. Unlike asteroids and comets native to our solar system, which orbit the Sun in relatively predictable paths, interstellar objects race through on hyperbolic trajectories. They might be visible for only days or weeks before they fade beyond our detection capabilities. by the time we recognize an object as interstellar and mobilize our observational resources, it might already be too faint to study in detail. We're trying to conduct a census of a population that's not only mostly invisible, but also constantly in motion, never staying still long enough for a careful count. The distribution of these invisible objects throughout our solar system is another unknown in our cosmic census. Are they uniformly distributed, or do they concentrate in certain regions? Gravitational focusing by the Sun might create regions where interstellar objects are more likely to be found. The giant planets, particularly Jupiter with its immense gravity, might act as lenses that focus or deflect interstellar objects in complex patterns. There might be rivers of higher density flowing through our solar system, paths that interstellar objects preferentially follow due to the combined gravitational influences of the Sun and planets. Some interstellar objects might be temporarily captured into long, elliptical orbits around the Sun, becoming quasi-residents of our solar system for thousands or millions of years before being ejected again. These temporarily captured objects would be even harder to distinguish from native solar system bodies. They might masquerade as long-period comets or distant asteroids, their true interstellar origin hidden by their current-bound orbits. How many of the comets we've observed over the centuries were actually interstellar visitors that had been temporarily captured? We may never know. The technological improvements on the horizon offer hope for a more complete cosmic census. The Vera Rubin Observatory, with its enormous camera and rapid survey capability, will photograph the entire visible sky every few nights. This unprecedented surveillance will dramatically increase our chances of detecting interstellar objects, potentially finding dozens or hundreds in the coming decade. Space-based telescopes operating in infrared will be able to detect the heat signatures of objects invisible in optical light. Networks of smaller telescopes working together will provide continuous coverage of larger areas of sky. But even with these improvements, we'll still be seeing only the tip of the iceberg. The smallest objects, the darkest objects, the most distant objects will remain invisible. We'll be conducting a census where we can only count a tiny fraction of the population and must infer the existence of the rest through statistical analysis and theoretical modeling. It's a humbling reminder of the limitations of our perspective, of how much of the universe remains hidden from our view despite our sophisticated technology. The implications of this incomplete census extend beyond mere counting. If millions of interstellar objects are passing through our solar system, they're having gravitational effects on the bodies we can see. These effects would be tiny for any individual object, but might accumulate over time. The orbits of comets in the Oort cloud might be perturbed by passing interstellar objects, occasionally sending comets toward the inner solar system. The distribution of objects in the Kuiper belt might be influenced by the cumulative gravitational effects of millions of interstellar passages over billions of years. Some researchers have suggested that we might be able to infer the presence of the invisible population through these indirect effects. By carefully studying the orbits of known solar system bodies, looking for anomalies that can't be explained by the gravitational influences of known planets, we might be able to detect the statistical signature of interstellar objects. It would be like inferring the presence of invisible fish in a pond by watching the ripples they create on the surface. We can't see the fish, but we can see their effects. The chemical and isotopic evidence might provide another way to census the invisible population. If interstellar objects occasionally collide with planets or moons, They would leave chemical signatures, unusual isotope ratios or exotic minerals that don't match the local composition. By searching for these signatures in lunar samples, meteorites, or impact craters on airless bodies, we might be able to estimate how many interstellar objects have hit our solar system over its history. Each impact would be a data point in our cosmic census, a record of an interstellar visitor that we can study even millions or billions of years after its arrival. The biological implications of this hidden population are intriguing. If millions of interstellar objects are passing through our solar system, and if some of them carry organic molecules or even preserved microorganisms, then the potential for panspermia, the spread of life between star systems, becomes more plausible. We might be living in a galaxy where life is constantly being shuffled between star systems by these invisible carriers, where the origin of life on any particular world might be traced back through a complex chain of interstellar transfers to some distant and unknowable source. The psychological impact of knowing we're surrounded by millions of invisible visitors from other stars is profound. It changes our perception of our place in the universe. We're not isolated on our pale blue dot, separated from the rest of the galaxy by vast distances. We're constantly being visited, constantly in contact with material from other star systems. Most of these visitors pass by unseen and unknown, but they're there nonetheless, silent witnesses to our existence, carriers of stories from places we'll never see. As our census-taking abilities improve, we might discover that the population of interstellar objects is even more diverse than we imagine. There might be classes of objects we haven't conceived of, objects formed in environments very different from our solar system, objects modified by passages near exotic stars or through extreme regions of space, objects that challenge our understanding of planetary formation and evolution. Each new discovery would add another row to our cosmic census, another category of visitor to account for. The frustration and wonder of this incomplete census is that we know we're missing most of the picture. It's like being an ancient cartographer trying to map the world while only being able to see a few miles from shore. We know there's more out there, vast continents of discovery waiting to be explored, but we can only guess at their nature based on the few fragments that wash up on our beaches. The invisible population of interstellar objects is a reminder of how much we still don't know, how many mysteries still wait to be discovered in the darkness between stars. Chapter 7. The Gravitational Dance of Wanderers. Every star's gravity creates ripples in space-time, gentle waves that extend far beyond the visible boundaries of stellar systems, reaching out into the darkness to guide cosmic travelers on their eternal journeys. When Borisov felt our sun's pull from far away, when its ancient trajectory began to bend ever so slightly toward our star, it was joining a dance that has been choreographed by gravity since the birth of our galaxy. These gravitational whispers orchestrate a complex ballet that we're only beginning to perceive, a cosmic performance where every object knows its steps even if we don't yet hear the music. To understand this gravitational dance, we must first appreciate the true reach of gravity. Unlike light, which can be blocked or absorbed, gravity extends infinitely through space, growing weaker with distance but never truly disappearing. Our sun's gravity doesn't stop at Neptune or at the edge of the Oort cloud. It continues outward, becoming ever more feeble but still present, still capable of influencing objects at distances we might consider impossibly remote. Right now, our sun is gravitationally tugging on objects light years away, and stars light years away are tugging on objects in our solar system. These influences are tiny, almost imperceptible, but given enough time, they accumulate into significant effects. When an interstellar object like Borisov approaches our solar system, it doesn't suddenly feel our sun's gravity at some defined boundary. Instead, the sun's influence grows gradually as the object approaches, a gentle pull that slowly becomes stronger, curving the object's path in a graceful arc. The mathematics of this interaction are beautifully precise. Every trajectory is a perfect conic section, a hyperbola for objects moving too fast to be captured, an ellipse for those that become bound. These shapes, described by Johannes Kepler 4 centuries ago for planets, apply equally to interstellar visitors, a universal language of motion written in the curves of space-time. But the dance is more complex than just the interaction between an interstellar object and our sun. The planets, especially massive Jupiter, add their own gravitational notes to the cosmic symphony. As Borisov passed through our solar system, it felt not just the sun's pull, but also the gentle tugs of all our planets. Jupiter, with its enormous mass, can significantly alter the trajectory of passing objects, sometimes capturing them into the solar system, sometimes flinging them out at even higher speeds. This gravitational assist, the same technique we use to accelerate our spacecraft to the outer planets, works equally well on natural objects, turning planets into cosmic slingshots that can dramatically change an object's speed and direction. The timing of these gravitational encounters matters enormously. If Borisov had arrived a few months earlier or later, if its trajectory had been slightly different, it might have passed closer to Jupiter and received a gravitational boost that would have sent it out of our solar system at a much higher speed. Or it might have been slowed enough to be captured into a long elliptical orbit, becoming a permanent resident of our solar system. The difference between escape and capture can be surprisingly small, a matter of a few kilometers per hour in velocity, a few million kilometers in position. The cosmic dance is precisely choreographed, and small variations in the steps can lead to dramatically different outcomes. This gravitational choreography extends beyond individual star systems to encompass our entire galaxy. Stars don't exist in isolation. They move through space in complex patterns, influenced by the combined gravity of billions of other stars, by massive molecular clouds, by the mysterious dark matter that makes up most of our galaxy's mass. These influences create a constantly changing gravitational landscape through which interstellar objects must navigate. A comet ejected from a star system millions of years ago has had its trajectory influenced by hundreds or thousands of stellar encounters, each one adding a small deflection that accumulates over time into a completely different path. The concept of gravitational focusing helps us understand why we might see interstellar objects coming preferentially from certain directions. Just as a lens focuses light, massive objects can focus the trajectories of smaller bodies. Our sun acts as a gravitational lens for interstellar objects, approaching from behind our direction of motion through the galaxy. Objects that would have missed our solar system are deflected toward us, increasing the flux of objects from that direction. This focusing effect means that the distribution of interstellar object approach directions isn't random, but carries information about our motion through the galaxy and the distribution of objects in our local galactic neighborhood. The three-body problem, one of the most famous challenges in celestial mechanics, becomes even more complex when dealing with interstellar objects. When an object passes through a star system, It's not just interacting with the star, but with all the planets, moons, asteroids, and comets in that system. These multiple gravitational influences create chaotic dynamics, where tiny differences in initial conditions can lead to vastly different outcomes. An interstellar object passing through a planetary system is like a ball in a cosmic pinball machine, bouncing off gravitational fields in ways that can be calculated precisely for short times, but become unpredictable over longer periods. Some interstellar objects might experience repeated encounters with the same star system. An object that passes through our solar system and is slightly deflected might, after millions of years wandering through space, encounter other stars that deflect it back toward us. These return visits would be extremely rare, requiring just the right combination of gravitational deflections. But in the vastness of time and space, even rare events occasionally occur. Imagine an interstellar comet that visits our solar system every 100 million years, a cosmic boomerang thrown by gravitational forces on scales we can barely comprehend. The role of binary and multiple star systems in the gravitational dance adds another layer of complexity. Most stars in our galaxy aren't alone like our Sun, but exist in binary or multiple star systems. When an interstellar object encounters such a system, the gravitational dynamics become even more complex. The object might be captured into a chaotic orbit around both stars, or it might be accelerated to extremely high velocities by a close encounter with one star while the other is nearby. Binary star systems are particularly efficient at ejecting objects at high speeds, acting as cosmic catapults that can fling comets and asteroids completely out of the galaxy. Stellar clusters, regions where hundreds or thousands of stars exist in close proximity, are particularly interesting environments for the gravitational dance. In these clusters, stars are close enough together that interstellar objects would experience frequent gravitational encounters. An object might ping-pong between stars, gaining and losing energy in a complex dance that could last millions of years. Some objects might be trapped in the cluster, orbiting not around any individual star but around the cluster's center of mass. Others might be accelerated to such high velocities that they escape not just the cluster but the galaxy itself, becoming intergalactic wanderers. The galactic tide, a subtle gravitational effect caused by the difference in the galaxy's pull on different parts of our solar system, plays a long-term role in the dance. This tide is incredibly weak, but over millions of years, it can significantly affect the orbits of objects in the outer solar system. For interstellar objects passing through, the galactic tide might be just strong enough to tip the balance between escape and capture. An object that would barely escape our solar system might be slowed just enough by the galactic tide to be captured into a long elliptical orbit. Resonances add a mathematical beauty to the gravitational dance. When orbital periods form simple ratios, gravitational influences can accumulate in regular patterns, creating stable configurations or causing dramatic changes. We see this in our own solar system, where Jupiter's moons dance in resonant chains, where gaps in the asteroid belt mark unstable resonances with Jupiter. Interstellar objects might occasionally be caught in temporary resonances with planets, their trajectories locked into mathematical relationships that persist for thousands of orbits before breaking apart. The concept of the restricted three-body problem helps us understand certain aspects of this dance. When an interstellar object is far from our solar system, it moves essentially in a straight line through space. As it approaches, it enters a region where the Sun's gravity dominates, following a hyperbolic orbit around our star. But there are special points, called Lagrange points, where the gravitational forces of the Sun and planets balance in such a way that objects can remain relatively stationary. While interstellar objects are moving too fast to be captured at these points, they might pass through them, experiencing unique gravitational conditions that could affect their trajectories in interesting ways. The gravitational dance extends to extremely long timescales through what astronomers call secular perturbations. These are slow, cumulative changes in orbits caused by the averaged gravitational influences of planets over many orbital periods. For a captured interstellar object, these secular perturbations could gradually change its orbit over millions of years, perhaps eventually ejecting it back into interstellar space or causing it to collide with a planet. The dance doesn't end with capture. It continues as long as the object remains in our solar system, a slow waltz of orbital evolution. Gravitational waves, ripples in space-time itself, predicted by Einstein and recently detected by instruments like LIGO, add an almost imperceptible but theoretically interesting aspect to the dance. While the gravitational waves from normal stellar encounters are far too weak to affect interstellar objects. Noticeably, extreme events like merging black holes or neutron stars could create waves strong enough to slightly perturb the trajectories of nearby objects. An interstellar object that passed near such an event would carry in its trajectory a record of that cosmic catastrophe, a gravitational memory of violence witnessed in its journey through space. The dance of wanderers also includes gravitational interactions between interstellar objects themselves. While space is vast and such encounters are rare, over billions of years some interstellar objects must occasionally pass close to each other. These encounters could dramatically alter both objects' trajectories, perhaps capturing one into orbit around the other, creating a binary interstellar object. Two cosmic wanderers bound together, dancing through the darkness between stars. Such binary objects, if they exist, would be fascinating targets for study, preserving information about the dynamics of interstellar space. The possibility of gravitational lensing by interstellar objects presents an intriguing observational opportunity. While individual objects are too small to create detectable lensing effects on starlight, a stream or cluster of objects might create subtle distortions that could be detected by precise photometric measurements. This would allow us to detect interstellar objects that are otherwise completely invisible, mapping the dark population through their gravitational effects on light from distant stars. The dance would be revealed not by seeing the dancers, but by watching how they bend the stage lights. When we consider that Borisov travelled for millions of years before reaching us, and will travel millions more after leaving our solar system behind, we begin to grasp the true scale of cosmic time in which these interstellar wanderers exist. In the timeline of the universe, our observation of Borisov was less than a heartbeat, a momentary flash of recognition between two travellers passing in the vast darkness. These objects have witnessed the birth and death of stars, the formation and destruction of planetary systems, the slow evolution of galaxies. They carry the history of the cosmos in their trajectories, stories written not in words but in orbital mechanics, in the subtle accumulation of gravitational influences over eons of time. To appreciate the deep time perspective of interstellar objects, let's first consider the age of Borisov itself. Based on its trajectory and velocity, Astronomers estimate it had been travelling for at least tens of millions of years before entering our solar system. But this is likely a vast underestimate. The object itself, the frozen nucleus of ice and dust that we briefly observed, probably formed billions of years ago in the protoplanetary disk of another star. It might be older than Earth, older than our Sun, a frozen artifact from an earlier epoch of our galaxy's history. When the materials that would become Borisov first condensed from the cosmic dust, our solar system might not have existed yet, or Earth might have been a molten ball of rock just beginning to cool. The journey of an interstellar object through deep time is a story of profound isolation punctuated by brief encounters. For millions of years, Borisov drifted through the darkness between stars, far from any source of heat or light. The temperature of its surface would have equilibrated with the cosmic microwave background radiation, just 2.7 degrees above absolute zero. In this profound cold, chemical reactions essentially stop, preserving the object in a state of suspended animation. The ice and dust that make up Borisov have been frozen in place for eons, a time capsule from another era waiting to be briefly awakened by the warmth of a passing star. During its journey through interstellar space, Borisov would have witnessed the evolution of our galaxy on scales that dwarf human comprehension. Stars that were young and bright when Borisov began its journey have since aged and died. Some have exploded as supernovae, enriching the interstellar medium with heavy elements. Others have collapsed into white dwarfs, neutron stars, or black holes. Stellar nurseries where new stars were being born have dispersed, their stellar children spreading across the galaxy. The spiral arms of our galaxy, those grand patterns of stars and gas that we see in astronomical images, have rotated and evolved, their shapes slowly changing over millions of years. The concept of stellar generations takes on new meaning from this deep time perspective. Our Sun is a third-generation star, formed from gas enriched by at least 2 previous generations of stellar nucleosynthesis. But Borisov might have formed around a second-generation star, or perhaps even one of the rare first-generation stars that formed from primordial hydrogen and helium. If so, its composition would be subtly different from objects in our solar system, carrying information about the chemical state of the galaxy billions of years ago. Each interstellar object is potentially a messenger from a different epoch of galactic evolution, preserving in its chemistry the conditions that existed when and where it formed. The paths of interstellar objects through deep time are not straight lines, but complex trajectories shaped by countless gravitational encounters. Over millions of years, an object like Borisov would have passed within the gravitational influence of hundreds or thousands of stars. Each encounter, even from distances of light years, would have slightly altered its trajectory. The cumulative effect of these encounters is to randomize the orbits of interstellar objects, erasing information about their specific origins while encoding information about the average gravitational environment of our galaxy. By the time Borisov reached us, its trajectory was the result of millions of years of gravitational processing, a path that tells us more about the journey than the destination. The deep time perspective also reveals the role of rare but significant events in shaping the population of interstellar objects. Supernovae, though rare on human timescales, are common over millions of years. An interstellar object passing within a few light years of a supernova would be subjected to intense radiation and possibly a blast wave of hot gas. This could alter its surface chemistry, trigger sublimation of volatile ices, or even fragment the object into smaller pieces. Galactic collisions, though taking hundreds of millions of years to unfold, could scatter vast numbers of objects from their parent systems, creating waves of interstellar wanderers that propagate across the galaxy. The oscillation of our solar system through the galactic disk adds another temporal rhythm to the story. With a period of about 70 million years, our solar system bobs up and down through the dense midplane of our galaxy's disk. When we pass through the midplane, we encounter denser regions of stars and gas, increasing the likelihood of gravitational encounters and potentially triggering comet showers from our own Oort cloud. Interstellar objects passing through our solar system during these times might experience different gravitational influences, different capture probabilities, different fates. The deep time perspective reveals these slow cosmic rhythms that are invisible on human timescales, but fundamental to understanding the long-term evolution of planetary systems. The survival of objects over deep time is itself remarkable. Space might seem empty, but over millions of years, even the thin interstellar medium can have significant effects. Interstellar dust grains traveling at tens of kilometers per second relative to an object like Borisov create a gentle sand-blasting effect that can erode surfaces over time. Cosmic rays create a steady bombardment of high-energy particles that can break molecular bonds and create new compounds. The pressure of starlight from all the stars in the galaxy, though incredibly weak, can gradually alter orbits over millions of years. That Borisov survived intact long enough to reach our solar system is testament to the resilience of these cosmic wanderers. From a deep time perspective, the exchange of material between star systems through interstellar objects is not exceptional, but routine. Over the 4.6 billion year history of our solar system, millions or billions of interstellar objects have likely passed through. Some would have collided with planets or moons, delivering exotic materials from other star systems. Others might have been captured, becoming permanent residents indistinguishable from native solar system bodies. This constant exchange means that our solar system is not a closed system that evolved in isolation, but an open system that has been exchanging material with the rest of the galaxy throughout its history. The implications for the origin and distribution of life become even more profound when viewed from this deep time perspective. If life arose on Earth 3.8 billion years ago, it has existed for almost a third of the age of the universe. During that time, countless objects have been ejected from our solar system by gravitational interactions, some potentially carrying microorganisms protected within rocks, blasted off Earth by impacts. These objects are now wandering the galaxy, potential seeds of life that could, given millions or billions of years, reach other star systems. Similarly, life that arose elsewhere billions of years ago might have sent its own ambassadors into interstellar space, some of which might have passed through our solar system. The deep time perspective transforms our understanding of what it means for an object to be from a particular star system. After millions of years of wandering, after countless gravitational encounters that have randomized its orbit, can we really say that Borisov is from any particular star? It has become a citizen of the galaxy, shaped as much by its journey as by its origin. The atoms that make up Borisov were forged in the nuclear furnaces of stars that died billions of years ago, assembled into molecules in the cold of interstellar space or a protoplanetary disk, frozen into a comet that was ejected from its parent system and then processed by millions of years of cosmic radiation. It is not from a place, but from a process that spans billions of years and encompasses much of our galaxy. The detection of objects like Borisov gives us a unique window into deep time. When we analyze the spectrum of an interstellar comet, we're not just studying its current composition, but reading a record of its entire history. The ratios of different isotopes tell us about the nuclear processes that created the atoms. The molecular composition tells us about the chemical environment where the object formed. The degree of processing by cosmic rays tells us something about how long the object has been traveling through space. Each observation is a glimpse into deep time, a fragment of cosmic history preserved in ice and stone. The future trajectories of objects like Borisov extend the deep time perspective forward as well as backward. Borisov will continue traveling through space for millions or billions of years to come. It might pass through other star systems, might be captured by another star, might collide with another planet. It might survive until the era of cosmic expansion accelerates to the point where galaxies are isolated from each other, becoming a lonely wanderer in an empty universe, or it might be destroyed tomorrow by a collision with another object. The uncertainty of its future is as vast as the certainty of its past is long. From the deepest time perspective, even the categories we use to classify objects begin to break down. Is Borisov a comet? It behaved like one when it passed through our solar system, developing a coma and tail as its ices sublimated. But for most of its existence, it has been an inert chunk of ice and rock, more like an asteroid, and if it's eventually captured by another star system, it might become active again, or it might remain frozen, depending on the nature of its orbit. The deep time perspective reveals that these classifications are temporary states rather than fixed identities, phases in a long existence that spans many different environments and conditions. The philosophical implications of the deep time perspective are profound. These objects have existed for periods that dwarf not just human lifespans, but the entire history of human civilization, the entire history of complex life on Earth. They will continue to exist long after our sun has died, long after our galaxy has collided with Andromeda, perhaps until the universe itself ends. In their patient journeys through space and time, they embody a kind of cosmic permanence that puts our brief existence into perspective. We are temporary observers of eternal wanderers, privileged to glimpse for a moment objects whose stories span eons. Chapter 9. The Quiet Truth of Cosmic Connection. What if Borisov wasn't alone, but part of an eternal procession we're finally able to see? As we reach the culmination of our cosmic contemplation, as perhaps you drift closer to sleep with these thoughts of infinite space and time, we arrive at a truth both simple and profound. These interstellar wanderers might be the universe's way of sharing itself with itself, a cosmic circulation system that connects all star systems across the vastness of space and the depths of time. In their silent passages, they remind us that all star systems are connected, that we're not isolated islands in space, but part of a vast, interconnected cosmic web where matter, energy, and perhaps even life flow between the stars in ways we're only beginning to understand. The discovery of Borisov and Oumuamua has fundamentally changed our perspective on our place in the universe. For all of human history, we looked at the stars as distant, unreachable points of light, separated from us by voids so vast that no material connection seemed possible. We imagined our solar system as a closed bubble, containing only the sun, planets, and smaller bodies that formed together 4.6 billion years ago. But now we know differently. We know that pieces of other star systems regularly pass through our cosmic neighborhood, that we can observe and study material that formed around alien suns, that the gulf between stars is bridged by these silent wanderers carrying their messages through the darkness. This cosmic connection operates on scales that challenge human intuition. The same comet that formed in the outer reaches of a star system 100 light-years away, billions of years ago, can pass close enough to Earth for us to study its composition with our telescopes. The atoms in that comet, forged in the nuclear furnace of a star that died before our sun was born, can enter our solar system and become part of our local environment. If that comet collides with a planet or moon, those atoms become permanently incorporated into our solar system. The iron in your blood, the calcium in your bones, the carbon in your DNA might include atoms that arrived on interstellar objects over the history of our solar system. The network of connections created by interstellar objects is impossibly complex. Every star system is both a source and a destination, ejecting its own objects while receiving visitors from elsewhere. The paths of these objects create an intricate web of trajectories connecting different regions of our galaxy across vast scales of space and time. A comet ejected from a star system in one spiral arm of our galaxy might, after millions of years of wandering, pass through a star system in a completely different spiral arm. Along the way, it might be deflected by dozens of other stars, each encounter adding another link to the chain of connections. This interconnectedness suggests that star systems might influence each other's evolution in ways we haven't fully appreciated. The delivery of volatile compounds by interstellar comets might affect the habitability of planets. The gravitational perturbations caused by passing interstellar objects might trigger comet showers that cause mass extinctions or deliver water to dry worlds. The exotic materials carried by these objects might catalyze chemical reactions that wouldn't otherwise occur. Each star system's development is potentially influenced by material and gravitational effects from many other systems, creating a galaxy-wide network of subtle interactions. The implications for the distribution of life throughout the galaxy are staggering. If life can survive the journey between stars protected inside rocks or ice, then interstellar objects become potential vectors for panspermia, a single genesis of life, perhaps billions of years ago in some long-dead star system, might have seeded thousands or millions of other systems through this network of interstellar objects. We might not be alone in the universe, not because life arose independently in many places, but because it arose once or a few times and then spread through the galaxy like seeds on a cosmic wind. Even if life itself doesn't survive the journey, the complex organic molecules that are the precursors to life certainly can. We know that comets in our own solar system carry amino acids, nucleotide bases, and other complex organics. Interstellar comets likely carry similar molecules, perhaps with subtle differences reflecting their formation in different chemical environments. As these objects pass through star systems, some of their organic cargo might be delivered to planets and moons, enriching their chemical inventory and potentially jump-starting the processes that lead to life. The galaxy might be continuously seeding itself with the ingredients for life, ensuring that wherever conditions are suitable, the necessary materials are available. The quiet truth of cosmic connection extends beyond material exchange to information transfer. Every interstellar object carries information about its parent system, the chemical composition, the formation conditions, the types of processes that operated there. By studying these objects, we're conducting astronomy by meteorite, learning about distant star systems not through telescopes, but through direct sampling of material from those systems. Each object is a data point in our understanding of how planetary systems form and evolve throughout the galaxy. This information transfer works in both directions. Objects ejected from our solar system carry information about our sun and planets to other star systems. Somewhere in the galaxy, perhaps right now, an alien civilization might be observing a comet that formed in our solar system, analyzing its composition, wondering about its origin. They would see the chemical signature of our sun, the isotope ratios that tell of our solar system's formation, perhaps even organic molecules that formed on or near Earth. We are unconsciously broadcasting information about our solar system throughout the galaxy through these ejected objects. The temporal aspect of this cosmic connection adds another dimension of profundity. The network of interstellar objects connects not just different places but different times. An object that formed 5 billion years ago, before our solar system existed, can deliver to us information about the early galaxy. An object we eject today might not reach another star system for 1 billion years, carrying to the future information about our current era. These objects are time machines, preserving and transporting information across eons, creating connections between epochs as well as locations. The realization that we're part of this cosmic network is both humbling and elevating. We're not special or unique in receiving interstellar visitors. Every star system experiences these passages. But we're also not isolated or alone. We're part of a galaxy-wide community of star systems exchanging material and information. Our solar system is both a node in this network and a participant in its evolution. We receive, we process, we transmit. We're part of a conversation that has been ongoing for billions of years and will continue for billions more. The quiet nature of this cosmic connection is perhaps its most profound aspect. There are no dramatic announcements, no cosmic fanfares. Objects drift in from the darkness, pass through our solar system, and drift back out into darkness. Most go unnoticed, invisible to our telescopes, unknown to our consciousness. But they're there nonetheless, silent ambassadors from distant stars, quiet reminders of our connection to the cosmos. The universe doesn't shout its connectivity. It whispers it in the gentle passage of these cosmic wanderers. This quiet truth transforms our understanding of what it means to be part of the universe. We're not merely in the universe, we're of it, connected to it through countless threads of matter and energy, space and time. The atoms in our bodies have been on incredible journeys, forged in stars, ejected into space, incorporated into new stars and planets, perhaps travelling between star systems on interstellar objects. We are temporary arrangements of atoms that have been circulating through the galaxy for billions of years and will continue to circulate for billions more. The discovery of this cosmic connection through interstellar objects is perhaps one of the most profound realizations of modern astronomy. It ranks with the discovery that stars are other suns, that galaxies are islands of stars, that the universe is expanding. Each of these discoveries expanded our perspective, showed us that the universe is larger, more complex, more interconnected than we imagined. The discovery of interstellar objects shows us that the final frontier isn't as empty as we thought, that the space between stars is crossed by countless wanderers, that star systems throughout the galaxy are connected in ways we're only beginning to understand. As we continue to discover more interstellar objects, as our technology improves and our understanding deepens, we'll undoubtedly uncover more aspects of this cosmic connection. We might find that certain types of objects are more common than others, suggesting universal processes in planetary system formation. We might discover objects with compositions so exotic that they force us to revise our theories of stellar and planetary evolution. We might even find objects that carry unambiguous biosignatures, proving that life exists elsewhere in the galaxy. But even without these future discoveries, the quiet truth remains. We are connected to the cosmos in ways both subtle and profound. Every star we see in the night sky has potentially sent objects through our solar system. Every star system in our galaxy is connected to every other through this network of wandering objects. The universe is not a collection of isolated systems, but a unified whole, connected across vast distances by these silent messengers. In this gentle truth, perhaps we find our place in the infinite dance of existence. We're not alone, not isolated, not separate from the cosmos. We're part of it, connected to it, in conversation with it through these quiet wanderers that pass through our solar system. Borisov was not just a visitor, but a reminder that the universe is more connected than we imagined, that star systems share their materials and their stories across the vastness of space, that we're all part of something larger and more wonderful than we can fully comprehend. And so, as you drift towards sleep with these thoughts of cosmic connection, remember that even in the darkness between stars, even in a vast emptiness of space, connections exist. Objects are traveling, carrying their ancient messages between star systems. Right now, as you rest, interstellar wanderers are passing through our solar system, invisible and unknown but present nonetheless. They've been passing through since before Earth formed, and they'll continue long after our sun has died. In their quiet passages, in their eternal journeys, they embody the truth that we're all connected, all part of the same cosmic story, all sharing in the same infinite dance of matter and energy, space and time. The universe whispers its connectivity through these cosmic wanderers, through Borisov and Oumuamua and the millions of objects we cannot see. It tells us that distance is not separation, that time is not isolation, that we're all part of a vast, interconnected, ever-evolving cosmos. And in that quiet truth, in that gentle reminder of our cosmic connection, perhaps we find not just scientific understanding, but a deeper sense of belonging, a peaceful recognition that we're home in the universe, connected to all of it, part of an eternal procession of matter and energy flowing between the stars.